Hello and welcome to the Chapter 9 notes, also known as the day a bunch of y'all skipped, and so I'm making you do work anyway. Or you had to go to sports things. Yay, sports. Making it hard to teach you since, I don't know, whatever. Wow, I don't sound positive. Okay, so today, well, I don't know if you know this, but last week when we journeyed into Chapter 8, we started the third part of the three parts in Statistics 1. So if you forgot, the first part was, can I describe data? And that was chapters 1 through 4, which were all about, means and standard deviations, and can I describe this distribution, and that stuff, and making graphs, describing things. And then we hit probability, which was, can I predict things? Woohoo! And then these two are going to come together and make a math baby known as inference. Now, the idea of inference is actually pretty simple if you think about it correctly. So let's see if I can draw a picture today. I want to use the pen, if it'll let me use the pen. Yeah. We have this big old group of people that represents our population. So just draw yourself like a little bean. Woohoo, population. And there's some things in the population that we want to know. Like maybe you want to know the proportion of your sales that are from new customers, or maybe you want to know the average age of your customers. These are things you want to know. And what we learned is what we learned in chapter 8 is finding out like that information is wicked hard. So instead what we do is, woohoo, we get a smaller bean, known as the sample, taken from the big bean. Now, I've tried to draw my beans that they look alike because they should look alike. Your sample, if it's a good one, should represent your population. So this is us taking a sample. Woohoo! The one rule for sampling is that we must sample well. The way we sample well is we make things random, because random equals out the chance that everybody be chosen. So if I've done a good job and I want my little bean to look my big bean, or my sample to look like my population, what I really need to do is use random sampling in some sort of method. So what we'll do instead is inside of our sample that was supposed to be underlining, we'll get the mean of the sample. So this is the average age of the sample of my customers, or I'll get the proportion in my sample. So the average age, or sorry, the proportion of my sales, which are from new customers, from the sample. And that's great and everything, but that information is just about the sample. This is what we were doing in the beginning of the class, finding means and other things of samples. What we want to do is we want to take the last step. We want to take sample stuff and use it to say things about populations. And that, my friends, is what inference, which that's not the right symbol. Can I do undo? Haha, winner. That did not work so well. Inference. Woo! Don't worry, I'm going to be typing the rest of this. Uh, maybe. What inference is all about is using statistics to predict parameters. Polite reminder, the blue stuff are statistics, the red stuff are parameters. So, that's what inference is all about. I want to find ways to use... Jesus, that does not look like words. Somebody help me. Just kidding. My pen's not working. I'm trying to do this with my mouth. Use statistics, the blue stuff, to estimate parameters. Yay! And so we're going to start studying that. And the big thing about it is that, well, that's the rest of the class. We're going to do two types of inference for two different types of data, and that's it. And that's barely scratching the surface of what inference is all about. In reality, we're going to do like two little itty bitty things with inference, and then the rest of it is left to stats 2. So don't think you know the whole story for this, you know just part of the story. And that's where we're at. So, in class we did an activity about building sampling distributions. And unfortunately, I can't do that activity on the internet, so we're going to do something a little similar. So this is an example that I usually do in the Stats 2 class simply because they've seen this before and it's a little bit easier to wrap your head around. But we're going to look at a bunch of different samples of different sizes and see what that looks like. So imagine you have a population with something you want to know about it, and there's only about a 20% chance that you are going to grab that something you're going to know. So what we're going to do, and I'm going to pull up some internets now. It's the wrong one. Obviously, I'm doing lots of things on the internet. Good times. I've included the website this is from just so you can see it. So what is this? Well, the population proportion, the thing I'm interested in, is a 0.2. And then I'm choosing samples of size 5. So what you need to picture is that I am going out into this population and choosing 5 people and asking them, do you have this thing? Maybe it's, oh no, this was the artificial intelligence one. So I'm going to give the artificial intelligence 5 questions and see, are you going to get it right? And it's going to get it right 20% of the time. So maybe it's going to get 1 right, maybe it's going to get 2 right, maybe it's going to get 3 right, maybe it's going to get 4 right, maybe it's going to get 5 right. And that's what I'm going to do. But I'm going to do that like 1,000 times. So I'm going to have it generate 1,000 samples and see what that looks like. Ta-da! So the bad thing about this is you need to picture these dots as bricks. So these are the heights of your histogram, if you will. So you notice 0 is an option. It could be the artificial intelligence gets none of it right. 0.2 is an option. That's 1/5. So it gets 1 out of 5 right. 0.4, 2 out of 5 right. 0.6, 3 out of 5 right. 0.8, which is 4 out of 5 right. And then no 0.1s, which would be getting all 5 questions right, which with such a low probability, that's pretty unlikely. So you look at this distribution, you notice that it has that lovely skewed to the right shape. And it looks like its mean is, it's a little bit like close to 0.2, which is kind of good because it's close to the actual true proportion of the population. So that's what it looks like. So there's not much we can do with this because the problem is you have no idea what the population looks like. I have no guesses. Could look like anything. And I grabbed all these samples in the hope that it would look like something I could work with. Doesn't look so good. All right, well, let's try a bigger sample. So now I'm going to choose size 10. So I'm going to give it 10 questions instead of 5 and have it do it 1,000 times. You really can only do this with a computer. Blah-da! Okay, let's take a look. So now I have more possibilities because there's 10 questions that could get 1 right, which would be 0.1, could be 2, could be 3, could be 4, could be 5. It looks like it made it up to 6 just barely here, but didn't get like 7, 8, 9, or 10 because those would be on the graph and they're not. And you look at this shape and you notice, ooh, that's looking a little bit more, nice, but it's still got a little bit of that skew rightness happening because that right tail is much larger. And my mean is close to the original proportion of the truth of the population. But it's, it's a little big, which is probably because of the skewness. Da-da-da-da. All right, last time. No, wait, sorry. Second to last time. Now I'm going to do size 20. So notice I've been doubling down, trying to make it closer and closer to what I want. Let's do 1,000 samples. Woohoo! Ooh, this one's pretty nice. Does this almost look like a shape you recognize? Oh, I hope so. I hope so. Notice the mean here came out exact. That's kind of magic, because out of the many, many times I've done this, that's happened very not often. So there you go. There's the mean right there. Good times. Let's try one more time. But now instead of doing size 20, let's do size 100. We're just going to, rather than doubling down, let's, make it much, much bigger. And then again, I'm going to just try to write 1,000 and see what happens. Ooh, okay. So I'm hoping what you've seen is the larger the sample size I have picked, the more normal this has looked. And the closer to the mean it's gotten. Now this one's a little bit off, but again, one of the things we know about samples is we have sampling error. Every sample looks different, and there's no way for me to get close. Well, for me to be sure that I have the truth. In this case, I know what the population proportion is. In reality, you won't. But I'm hoping you've seen something from this pattern. So I'm going to start moving to smallest to largest. So this one, not very normal looking. Pretty good estimate for the mean. Yeah. And my spread goes from 0 to 1. All right. Then I up my sample size. My spread goes from 0 to about 0.6, so it's smaller. My mean is closer, but I'm a little over it now. I'm skewed still, so not much I can do with that. Here I'm looking normal-er. I'm still got some skew to one side, but not by much. My mean is perfect, and my spread has shrunk again. Now it went from 1 to 0.6 to now 0.45, and then last but not leastly, hey, it looks normal. And why do we want normal? Because on normal, we know how to do all the probabilities, and that's exactly why we want normal. I'm very close to my mean, And my spread is from 0.14 to 0.26, so it's about 0.22. So it's the smallest there is. So what happens? My center of my distribution, the mean of the distribution, gets really close to the population proportion. So what we're going to do is we're going to build these things and then use their mean to estimate the proportion. The next thing we notice is it looks more normal the larger the sample size. We're going to have some things to say about that and what you actually need to make it look normal. Because if you remember, this second one was pretty close. There's some secrets behind that. They're not secrets. I'm going to tell you what they are, so they're just secrets for now. And then the last thing we notice is that the spread got smaller and smaller and smaller the larger my sample size got. Let's get into describing that. All right. What we just built is what's called the sampling distribution. Da 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 da. So, here's what you need to know. Under certain conditions, the sampling distribution. I am writing the wrong thing. That's the next one. I haven't told you what the sampling distribution is. I should probably cut that out. Okay, the sampling distribution. Instead of one sample p, so remember we call this p hat, but I'm going to type it so I don't have to write the symbol. We gather many of the same size and look at the distribution of samples. So there are some consequences to this. So be aware that you no longer can do individuals, you have to do groups. So when you think about this, I can no longer ask things like, oh, what's the probability that one student is left-handed? I can now do what's the probability that one out of a group of 5 students is left-handed. So I have to do everything in groups. And that, changes some stuff. So we're going to see when we do this with means in about 2 weeks that I'll be able to do things like, oh, well, what's the average score of the golf team? But I won't be able to do what's the average score of just one player. So it's going to be interesting. It's a little different. All right, let's talk about the sampling distribution. So under certain conditions, and we'll get into those conditions. I'm not like keeping this away from you. I just want to focus on what it looks like. The sampling distribution, good typing, will be normal. And here's the things you need to know about it. It's going to look normal, which is awesome because we just saw that. God, typing this is so much worse. It will have mean. So the center of it will just be p, your proportion, or p hat, because you might be stuck using that instead. And the standard deviation will be, and I'm going to try to draw this because that's the only way this is going to go in, woohoo, is the square root. Oh, come on. I want to draw. It's screwing up. Of p q over n. God, that looks terrible. So as you look at this, its spread gets smaller as the sample size gets bigger. That was that part of n is the sample size, p is your probability of success, and q, as you may remember, is your probability of failure, which is 1 minus p. We're going to do some examples with this that will hopefully make this be a little bit better. Oh, I didn't think it would do that if I hit a button. Sorry. And I'm hoping this looks familiar. It looks a lot like the normal approximation of the binomial. The normal approximation for the binomial, as you may remember, is individuals. And with the sampling distribution, we're doing groups of size n. So essentially all you're doing is taking the normal approximation of the binomial and dividing by n to get this. That's it. Just averaging it across the group instead of doing just one person. Alrighty, let's do an example because that will probably help you much more than me just telling you what this is. So that's the object we're going to be dealing with, looking at groups, and then trying to use that to build something. So suppose the true proportion of college students who have taken at least one online course is 0.22. This data is kind of old. It's probably much higher now. It's probably closer to probably like, I guess, 2/3. We're going to look at a sample of 500 students. What would you expect the shape of the sampling distribution for the sample proportion to look like? Well, at that large, I think this is going to look normal. Woohoo! Because that's also the only thing I've told you. Yep, this looks normal. What else? Well, what's the mean going to be? The mean is just going to be the proportion. The mean is just going to be your p, which is 0.22. That's it. Ta-da! Here's the harder one. What's the standard deviation? I'm wondering how I'm going to make this fit. Let's find out. The standard deviation of p hat. I should have been writing this the entire time, by the way. And the mean is, well, the mean is the mean of the p hats. This is why we should come to class. How can I write this? I'm going to write square root in code. So square root of, now I got to be careful. I need my p, which is 0.22, times my q, which is going to be 0.78, divided by my sample size, which in this case I'm dealing with a sample of 500 students. When you calculate that out, you should get 0.8, or sorry, 0.01856. Pretty tiny. These are going to be small. Don't round these too much, or else you'll definitely get some wrong answers. Think about what's going on here. I've got something smaller than 1, something smaller than 1, and I'm dividing by something huge and then taking the square root. These are always going to be tiny. So if you're one of those people who likes to round like the devil, maybe resist your urges. There you go. Ha! I think I'm funny. I'm going to pause for a second. Sorry, I just really wanted to change p hat to p hat because that looked weird, because I also want to write this. So here's the thing. What I should be writing is I'm doing the mean of a sample. So this should really be, and this is going to look strange because I'm using the equation editor. Oh, that looks so horrible. Go to the edge, parenthesis. That's what I want. I want to do the mean of my samples. So remember, samples is like p hat, so sample proportion. So I'm going to grab this and put the appropriate symbols in here, if it'll let me. Pew! There we go. So what this is saying is I want the mean of the samples, so the sampling distribution mean, which is 0.22. And here it's saying I want the standard deviation of the sample proportions, which is this. Anyway, why do I want to bring that up? Because right about here, I'm going to need it. So I want to do the probability that looking at my sample, at least 25% have taken online class. So I want to know the probability that my sample, p hat, woo, is going to be greater than, because it's at least, it's the smallest it is 0.25, 0.25. And at this point, you should look at this and be like, I think I know how to do that. I know some things about probability. I need Minitabs! Woohoo! So I'm going to pull Minitab to the side and kind of small in a second. I should have had this open already. Because I only need parts of Minitab. Yes, I do many things. No! I fail at putting things together. You can see this good enough, I hope. So I'm hitting the graph button because I'm just doing probability. Going down to probability distribution plot. Going to view probability, the VP of probability. This is normal! Normal. What's my mean? Oh, it's that thing. 2.22. I hope this is big enough to where you can see it because mine looks kind of tiny. That thing. What's the standard deviation? Oh, that's that 0.08 stuff I found earlier. 0.01852. Woohoo! And then I want to figure out the probability that this distribution is going to be greater than, so stuff bigger, right tail, 0.25. And then I hit OK. And that's it. Oh no, Minitab, you have my answer. I hit the wrong button again. 0.05263. I love it when I have to read numbers out loud and fail at it. I have forgotten what this is already. My memory is great. Okay, that was fun. So again, talking about samples and proportions and being bigger than or smaller than, still doing probability. Let's take a look at this one. The probability, oh, that's not blue. The probability, my sample is less than 100, so p hat again, less than 100 of them. And you should be like, that's going to be all of them, because the biggest a proportion can get is 1. So there's something wrong here. Oh no, panic. Notice they're talking about the number of students here, 100, not a proportion. But it's 100 out of the 500, so I need to divide this by 500. And those of you who know your fractions really well recognize that this is the probability that my proportion is less than 0.20. Oops, too many zeros. Yay! So let's go back to mini stab. Let's move this over a little bit so I can see it. That's not what I wanted, Word. Word is so bad about knowing what I want. Word. Gonna hit edit last dialog because I'm still on this normal distribution with this specific mean and standard deviation. I'm gonna do left tail this time and 0.2. Woohoo! Well, that's a nice number. 0.1401. I bet you I picked that because I liked it. Okay, if my sample size increased to 1,000, what would change? And you go back and look at the setup at this, and you're like, where did I use sample size? Ta-da! Da-da-da-da! It appears to be standard deviation. So if I made this 1,000, this would go up. My sample size would go up, and therefore my standard deviation would go down, because my standard deviation has sample size in the denominator. So if I change this to 1,000, and I'm going to go a little slow here because I'm sure some of you are writing this down at this moment. 0, 1, 3, 0, 9, 6, 6. And I want to put these both on the screen if I can. I might have to zoom out a little. Hold on. There we go. So if you look at this, if I double what's in my denominator, I don't get half, because 2 in the denominator, you might think half. That square root is there. So what's really happening here, you got to be careful. If I wanted to have my standard deviation or my spread, I would actually need to quart this because, 4 times as much, because the square root of 4 is 2. Complicated, right? This is one of the reasons why sampling is so difficult, because to get a good or small spread, you have to do so large to have it happen. And it's a little dangerous. Moving on. So when can I do this? What are my conditions for using the sampling distribution? Going back to red because we're doing notes again. Have you noticed I color code things? I don't know. So when we talk about randomization condition, this was just making sure you have a good sample. So all samples must be gathered using a sampling method that has randomness in it. I don't know if you can hear my bird yelling, but one of them is. In it. Ooh, I wrote in it twice. So just be thinking things like the simple random sample, stratified, clustered, they all have random components. Or you can use one of the other methods and then multi-stage it by throwing some simple random sample or something else on top of it to make it so that you have randomness and meet this condition. This is one you maybe didn't see coming, and it's the 10% condition. This is to prevent what we call oversampling. So your sample size, which is a polite reminder that's little n, oops, must be less than 10% of the population. Basically what happens if you oversample and get something that's too big is you end up with something that looks more like the population. And if your population isn't normal, then this will not look normal and you'll have a bad estimate for the mean. Now, if you were in class, we actually did this. The second example I did was way oversampled. And what happened is we got something that was really, really non-normal looking. In fact, it looked almost uniform, which means everything looked the same. So it can happen to you. Don't let it be you. Make sure your population is, enormous and that your sample is big enough but not too big is basically what's happening. All right, and this is why my 20 worked pretty good, but my 100 was better with my computer example. There's that success failure condition. Yay! So our number of successes, aka NP, must be greater than or equal to 10, and your number of failures, aka n times q, must be greater than or equal to 10 as well. Oops. Remember, if it's not bigger than this, it might not work. Like, it won't look normal. That's one of the reasons why when I was looking at the internet's example, where is it? Lost it again. Ta-da! 100 was good because 100 times 20 is 20. 20 was close because 20 times 0.2 is going to give you like 4. Yeah, that's not big enough. That's why this isn't quite normal. It's close though. Ew. Why did I say ew? That didn't even make sense. N, P, and Q. See how the Q looks like the flip of the P? Dyslexia. difficulties. Let's talk about something kind of depressing. So let's assume the true proportion of college students who do not have dental insurance is 0.85. That's fun. Does this meet the success and failure condition? Yay! So I'm going to check success first. Oops. Gotta color code it. And that's going to be n times p, which is, how many of these do I have? 200 people times 0.85, which mathing it up, that should be 170. Yeah, double and then, yeah, okay. And that's greater than 10 by like a lot, so that's good. Thumbs up if I had a thumbs up symbol. Let's check failure. So this is going to be n times q. Sorry, I had a hard time finding a keyboard to q. So 200 times 1 minus 0.85, so 0.15. So double, move the decimal place, that's 30. That's definitely bigger than 10. Yay! Good to go. We checked one of the conditions. Notice I didn't check the other two here, because as you look through this, it just says a sample. It's not random. This isn't going to pass, but we're going to do it anyway. Cool. That's really lame. What's the probability the sample proportion will be less than 80? So what I'm saying is let's find a proportion in the sample and it being less than 80. So first I need my mean to do this, because I got to build my distribution. And my mean is just my proportion, so that's 0.85. And then I need my standard deviation, which I'm going to need. Oh yeah, I'm going to have to do a root. So again, I'm going to use some code to make it look like a root. So we're going to do square root, squirt. That's what I used to joke it was, because it looks like squirt. 0.85 times 0.15 divided by 200. Ta-da! And this is really tiny if I remember correctly. I'm going to have to look over it at 0.0252. Oof, I'm rounding that one kind of a lot. Oh well, live with it! Live with it! Alright, and then I'm looking for the probability that my sample proportion will be less than 80%, so 0.8. 0. Although I'm having a hard time getting the 0 to come up. That was weird. Let's go to Ministab. Alright, so now I'm dealing with a slightly different situation here. I gotta go to my last dialogue. I have a different mean, 0.85, and a different standard deviation. Woohoo! Let's check out our shaded area. I want to be less than, so I'm going to use left tail, 0.8. Hopefully that wasn't too fast. I'm going to hit OK. Da-da-da-da. Oh, every time I click in here it goes away. I wonder if I can copy and paste that. 02362. Yep. All right. Onwards and upwards we go. What's the probability that my sample proportion will be at least 85? So the smallest it is 0.85. Remember, with the normal distribution, it's continuous, so I don't need an equal to here. I can, use less than the whole, or greater than the entire way, and it won't matter at all. If you remember, 0.85 is the mean, so this is saying what's the probability that you're bigger than the mean? Well, that's half the distribution. I do not need Minitab to do that. Ta-da! All right. Okay, evidently I didn't have anything after that. Last up, next up? No. Words. What's the probability that in a sample of 200 students there will be between 160 and 180 that have dental insurance? So 160 between and 180. And then you look at this and you're like, that seems wrong because that's proportion. And, it's not a proportion. I got to divide by 200. Remember, proportions are always some kind of count out of a total. So I got to do that real quick. And, oh, I don't need to use my calculator. You know why? Because I wrote these down. They're 80 and 90. And put my proportion in the middle because it's between those two. And let's pull out some Minitab. So here I'm going to choose middle. Same distribution so I don't change anything. Between 0.8 and 0.9. Lovely. We're going to hit OK. And there's our probability. That's kind of a lot of stuff. 0.9528. Woohoo! So between 80% and 90% of students have, well, there's a 95.28% probability that between 160 and 180 of the 200 students have dental insurance. Ooh, that's a mouthful. That's funny because it's dental insurance. Okay, no, I just had to explain the joke. That was bad. All right. Let's check ourselves before we wreck ourselves. This is one of my favorite things to do, as you know. So we're going to look at this scenario and ask ourselves, are the conditions for the sampling distribution met? Ooh, let's read the scenario. I'm going to read out loud because I'm talking to myself, not in a room by myself. In early 2007, notice this before the market crash, mortgage lenders associations reported that homeowners were defaulting at record numbers. Or maybe this was right at the beginning of it. This is, okay. The foreclosure rate of 1.6% meant that millions of families were in jeopardy of losing their homes. Suppose a large bank holds 1,731 mortgages. So I immediately see a problem with this, but let's see how long it takes us to check all these. So the first thing we need to check is it random? And the answer is no. They are all from the same bank and there's no sample even taken. So that was our first failure. Here's our second failure. Or no, wait, this'll be fine. Is it 10% condition? Okay. I'm checking them all just because, that's who I am as a person and a teacher. So, is it 10%? So, what you're asking is 1,731 mortgages more than all the mortgages in the entire United States. And the answer to that is simply no, which means this is fine. So, this condition is met because 1,731 is not more than 10% of all mortgages. I love that mortgages has the word mort in it, which literally means dead. Buying a house will kill you. Yep. All right. Last but not leastly, success and failure. I've already done that one once, so I'm not going to this time. But I'm hoping you get the point. When it comes to checking these, you need just to ask yourself, is it reasonable that my sample is more than 10% of my population? And then, is my sample random? Let's look at a voting example. Voting is always kind of fun and weird. So here I'm going to look at a scenario where the local newspaper does a poll of a random sample of 330 voters, and 144 of them say they will vote yes on the school budget. So remember, this is a sample, not the population. Based on the sample, what's the estimate for the proportion of those who plan to vote yes? So all I've got right now is this sample. So that's my best estimate. My sample is, wow, that's really far over. There's some weird things happening with my adjustments here. 134, 144, 330. Magic. And if you do the division on that, you get, I'm going to round this because the number is kind of long. The 3 6 is repeating, but I'm going to round it because I'm going to need to. So my best guess is it's 43.6%. So that's close to majority. What really we look for in most elections is what we call plurality, which is more than half of the people vote yes on something, and that's what most budgets need to pass. And this is close, so we have a sample. We don't have the entire population. But what we want to do is we want to use that sample to estimate what the population might be. So here we go. We're going to use the 68, 90, 95, 99.7 rule to determine a margin of error for the estimate. So how far off I'm willing to be. So since I'm at 95%, I'm going to be using 2 because that's 2 standard deviations away. So margin of error, or how far off I'm willing to be, is 2 standard deviations away. So I didn't calculate standard deviation yet. I'm going to need to. Woohoo! So I got to do 2 times, let me write that star in there again just so I have the time symbol. The square root of my p, which I don't have the population proportions, I'm just going to use the sample one, times q, which would be just 1 minus p, 0.563. Sorry, I was trying to do that in my head. Oh, it's 4. good at mathing. Mostly subtracting is my thing. Divided by my sample size, which is 330. And that's going to be kind of tiny. So be careful with yourselves. So how far off am I willing to be? 0.0546. I'm rounding this one also, but one more decimal place than the other one for some reason. Okay, so I'm off by about if I look 2 standard deviations in each direction, that's about 5% roughly. So I'm saying that my estimate for what it's going to be is 43.6%, and then 95% of all samples will be within 5 standard deviations away. Or sorry, 5% away, not 5 standard deviations away. Oh, so I'm going to use the margin of error to do a little thing now called a confidence interval. So I haven't defined what this is yet, but I'm going to. For the proportion of people that plan to vote yes on the budget. So this just gives me an estimate of what's happening here. So how do I do this? I take 0.436 and I add and subtract. So I'm going to steal that symbol real quick. Insert symbol plus minus. This isn't blue. Jeez. My margin of error to this to see how far it goes in each direction. So what you go through and do this with the plus or minuses, I have to do minus for the lower end. And then plus for the upper end. And when you do that, you get an interval from 3814 to 4906. And I am doing some rounding with this, and there's some squiffy parts, but hopefully this is okay. Okay, so you look at this, and you're like, okay, so I'm 95% confident that when I look at people that are planning to vote yes, the biggest it's going to be is 49%. So it's not going to pass. It's not going to hit 50 or above. And that's what this is telling me. The 95% of the time, all the proportions will be between these two. Or this is a nice estimate for our mean, the center of that distribution, since 95% of all proportions will lie between these two. There's still a 5% chance I'm wrong, though, so there's that. We're only 95% confident based on our 2 standard deviations away. And that's another thing is like, I used 2. Is that really 95? No. I really should use the z-table to do the 95%er, so I really should fix that and do this properly. So let's use Minitab to help us out here. So I'm going to go to Graph, Probability Distribution Plot. For some reason I'm doing that, unlike the last few times. I want to look at the standard normal, which is mean 0, standard deviation 1. We go to shaded area, and here I want 95, so I want 5% in each tail, and that gives me something wrong. That, okay, 95% in each tail would be, oh, I'm on X value. That would be Y. 5% in each tail. Done. Oh, look at that. 1.96. So that's what I'm going to use instead. So I'm going to go back to this. I'm going to steal just the first part. So my margin of error is incorrect. I shouldn't be using this value. I shouldn't be using 2. I should be using 1.96 times, and this is my spread. I calculated it separately so that I could use it now. Did you notice my pause that time? Probably not. Getting better. All right. So when you do the add and subtract to this one, you end up with 0.3825 and 0.4895. So we got farther away from 49%. Remember, it could be any value in this interval. This is my total prediction. So it could be as low as like this. It could be so small it's down to like just above 38%, but it could be as big as 48.95, which is still not majority. So this is definitely not going to pass. So what you need to do is look at this and say, okay, I'm 95% confident that the percentage of people that are actually going to vote yes is somewhere between 38.25% and 48.95%. The budget is not going to pass. So we just took the sampling distribution and used it to make a prediction about what the population is going to do. This is our first tool behind inference, the confidence interval. Woohoo! Okay, so I'm going to pick up next time and our class with calculating confidence intervals and all the math behind it, so that should be fun. Uh, that's all I got. Hope it was clear.